Welcome to How to Build a Time Machine, Compensating for Latency in Streaming Games. My name is Morgan Brown. I'm a principal software engineer on game streaming, and I'm also a periodic speedrunner, which is part of why I'm interested in latency. So today, we're going to talk through Xbox Game Streaming 101, get into some latency basics, and then talk about how to mitigate it. Okay, so Game Streaming 101. Let's start with a story. Flying saucers have appeared above the Earth. They challenge Earth's greatest champion, Alex, to a game with the fate of the planet in the balance. Alex is far from home. How will they ever save the Earth? With Xbox Game Streaming. So I'm going to talk about game streaming today. There are two different flavors that you might have heard about. There's cloud streaming. That's where you stream games from Xbox consoles hosted in Azure. And there's remote play, where you stream games from your own Xbox. But because they're the same technology, everything we talk about today will apply equally to both. The idea is that you can play where you want on your choice of devices, and it's available right now. Sign up for the app or talk to your Microsoft representative for developer access. And if you are one of those developers, I have good news for you. Your Xbox game can stream with absolutely no changes. That's because cloud servers are just Xbox consoles modified for things like the power and cooling requirements of data centers. And every home console is a server for remote play. But the better news is you can make changes to your game for standout player experiences. Okay, so let's launch into some latency basics and get back to our story. Alex launches Game Pass, and in mere seconds, the game is running. Their accuracy is incredible, but something's wrong. Somehow, close shots are missing. The aliens, who cleverly brought their own Xbox, aren't as good, but their shots aren't missing. Could this be latency? Let's take a look at what that can look like. Here, we're going to take a look at a slow motion video of a game that's streaming, and we've added some artificial latency to it. What we're going to watch for is when you see a camera flash, that means the fire button is being pressed on the controller. And when the reticule flashes red, the game has received the button press. So let's take a look. There's the button press. And there's the red reticule when the shot gets received, and we've missed the ship. Okay, so when I'm talking about latency in this talk, what I mean is the time from when a player tries to do something until that thing actually happens for them. So for example, if they press a button at t equals 10 milliseconds and they see their character jump at t equals 30 milliseconds, do the subtraction, and we get 20 milliseconds. You might also sometimes see latency referred to as lag, but I'm not going to use that term. It sometimes is used to refer to other things as well. So why does it make a difference? Well, sometimes latency isn't fair. It can take a conscious adjustment, realizing what the timing has to be between when you press a button and when things are happening on the screen. And it can also feel like a penalty for playing well when you're pretty sure you did the right thing, and it just seems like the game doesn't agree. Now I'm going to pause and note that latency isn't by any means new to streaming. Single-player games have latency. That's from things like TVs with display latency. Controllers take some time, and human brains add a chunk of latency. And of course, with multiplayer, you get the introduction of network latency that adds latency between players, backend servers, and other players. So, for example, those who have played early first-person shooters, you might remember having to aim ahead of your target instead of at them, and that was because of latency. Now, before we get too far into streaming, I'm going to note quickly that, of course, the best latency mitigation is just to have less of it. And as the game developer, you can't change the network, but you may be able to optimize your game for latency, and especially when it's streaming. So for example, when it's streaming, you might choose your game's 60 FPS performance mode over a 30 FPS quality mode. Okay, so when we are streaming, what does this look like? Let's walk through the loop of a player's experience. So starting in the upper left, they can press a button on a controller. That button press has to get to the device they're playing on. Here, we're talking about a phone. So that could come over Bluetooth or USB or over a custom wireless protocol. And we find that time for those can vary, where Bluetooth is usually the slowest, USB is usually the fastest. And then in order to stream it, that button press has to get sent from the device to the Xbox. And that's over a network, which can vary. We'll get into more of that in a minute. Then it gets into the game loop. The game loop is for a 60 FPS game, perhaps going to be 16 milliseconds, but it could also be longer due to things like pipelining or frame drops. So then the game's going to render a frame, and in order to send that back, the Xbox server needs to encode it. The encode can take a variable amount of time based on the complexity of the scene, and then it gets sent back over the network. And then in order to display it, the client device needs to decode it. That decode can also take a variable amount of time, depending on the size of the frame and how fast the client device is. Then it needs to get it up onto the screen. Displays actually have very different amounts of latency. It can vary from a fast gaming monitor to a slower TV that isn't in gaming mode. There's just a tiny little speed of light delay getting from the display to the player's eyeballs. And then give or take about 250 milliseconds of time for the player to process what they've just seen and react to it. So when we're talking about network latency, what are the sort of key factors? Well, the biggest one is the distance between you and the Xbox running the game. So for cloud gaming, we optimize the distance to Xbox servers by locating them in Azure data centers around the world and automatically pairing players with the closest servers. When you're running remote play, of course, we can't control that. It's the distance between you and your house. Another important factor is your endpoint connection quality. So we think Ethernet is better than Wi-Fi, is better than 5G, is better than LTE. And we've also found that 5 gigahertz Wi-Fi can be a whole lot better than 2.4 gigahertz Wi-Fi. I mentioned earlier that I'd added artificial latency to that flying saucer video. The way I did that is with the XB stress tool that's included in the GDK. That lets us add artificial stream latency on a dev kit. There's an example command here where you can add average latency for a game stream, but there are lots of other options as well to try different scenarios. If you want to try latency from the cloud, talk to your Microsoft representative about a private offering for your game. Now let's talk about what we do about latency and get back to our story. With Alex's shots missing, all seemed lost. That is, unless the world's game developers could devise a way to compensate for Alex's network latency. So the idea here for mitigating stream added latency, that's that extra time, that extra network encode and decode time, is we want to start with the techniques that have been successful in single and multiplayer games already for mitigating latency, and then incorporate stream measurement and metadata APIs to cover the whole picture. So let's start with average latency. We have an API for that. It's called xGame Streaming Get Stream Added Latency, and it's for getting your average stream added latency over the last few seconds, and we think it's great for widening reaction windows. So here's what I mean by that. Gears 5 has a mechanic called active reload. We're going to show off what that looks like. Here's a successful one. Watch in the upper right-hand corner. It's going to run twice. Watch for the moving bar and the flash.
Watch it! Swarm!
Okay, so what we saw there is we hit the button right as the thing moved on to the target, and as a result, we got a flash, we got a faster reload, and our bullets are going to do more damage. Now, let's take a look at what happens if we're too late instead.
Not now!
Okay, so that time, because we were too late, it flashed red, our gun jammed, and our character got mad at us. And we wouldn't want that to happen because of latency. So to make it feel better when it's streaming, the Gears team found that using average latency to widen the window to get an active reload made the game feel better. Widening reaction windows is a good way to make timed interactions feel better, but for some scenarios, that's not the best match. This graph is my ping time to a data center over a cell network near my house. It shows that latency can vary even over a short time. If you need more precise information about the frame, we have more precise APIs to talk about. But first, back to our story. With the game's more generous scoring, more of Alex's shots hit true, and the Earth score soared. Still, sometimes a little network slowdown would rob Alex of perfection. Scientists and game developers agreed there was only one way to be sure Earth would be saved: build a time machine. Alex's shots would be sent back in time a fraction of a second, exactly enough to cancel out that dastardly latency, and the aliens would never notice. So, in order to build that time machine, we have to work with two timelines. One is the player reacting to what's on their screen, and the other is the game reacting to player input. Those are pretty close when you're playing in your living room, but when you're streaming, they diverge, and our goal is to merge the timelines. So to do that, we're going to build a time machine in these 6 easy steps. So let's get into them. Let's start with some starter code. This is code from the GDK sample for the Flying Saucer game. And here you can see we're looping through the flying saucers and checking collision for each of them. Straightforward enough. Okay, so first, in order to change history, we have to remember it. And in order to do that, what we're going to do is keep a map of the frame token that we got when rendering a frame to anything important about that frame. In this case, where the flying saucers and the target were on a particular frame. You might also notice we're using a circular buffer to help manage the memory of all of this. Next up, what we have to do is keep the game running while we wait for input. So that's to say, just do what you do. Keep running animations, enemies, and so forth. And to make it look better, maybe even consider client prediction of the player to keep the visuals smooth. But the important thing here is don't commit to anything. So for example, if the player gets hit, don't kill them, because maybe it will turn out that they actually moved out of the way at the last second. Okay, step 3. Let's match the input to a frame. Here we're using XGame streaming getAssociatedFrame, which ties the frame on the player's screen to the input that you just got. You could also use XGame streaming getLastFrameDisplayed to get a frame token for the most recent one if there's no input. We'll show a scenario for that later. Next up, we have to travel back in time. And what I mean by that is we need to combine the state of that frame from the past with the input that we just got to calculate what really happened from the player's perspective on that frame. So here we're finding the frame, and then we're getting the relevant data out of it. Next up, we have to render based on that recalculated state. So here's our collision code again from the example, but this time, instead of using the latest version of the state, we're using the one that we pulled out of our history. And step 6, victory. Okay, so here's what that looks like. Again, we're going to take a look in slow motion, watching for the flash when the player presses the button and the red flash on the reticule. There's the button press, and the input gets received. This time we got both of the ships. One other thing that I'll point out here, take a look at that explosion in the lower left corner. It's a little bit clear of the reticule, and that's on purpose for demonstration purposes. The ship kept moving while we were waiting for inputs, and we put the explosion in the last place that we saw it. However, you could imagine moving it back towards the reticule to make it look smoother for players. So let's talk about another idea, which is that no input is input 2. Or in other words, knowing right when the player is out of time to react to something is fair. And the API that we're going to use to do that is XGame streaming getLastFrameDisplayed. And for an example, we're going to talk about one of my favorite game development terms, Coyote Time, named after a certain coyote known for running out over cliffs, taking a look around, realizing it's out over a cliff, and then falling. So here are our two timelines for a game like that. On the left, we've got the server, or the game timeline, where the player is hanging out over a cliff, and on the client timeline, or what the player is seeing, they're still on the ledge. Now, a game might drop the character right now, but if so, the player would think that's unfair because they might have had a chance to react. So instead, what we're going to do as we move on to the next frame is we're going to leave the character hanging right there in the air where we left them. And in the meanwhile, the client gets to move forward, have another frame, another chance to react. But let's say that they don't react, and we move on to the next frame. Okay, now what happens is the character is out over the edge from the player's perspective, which is to say they're out of time. And what's happening on this frame and every frame is that the client is sending an acknowledgement back to the game that a particular frame was presented. And you can see that using the XGameStreaming getLastFrameDisplayed API. And using that, you can see that now that the player has seen this, the game can continue and drop the player. It's going to take a couple of frames for that to actually get back there, but a couple of frames later, what we see is the server drops the player, the client is at the end of their time, and it was fair. Okay. Now let's talk briefly about multiplayer. And on a little bit of a tangent, one of my favorite game streaming bugs was a game that didn't expect to get a 0 millisecond ping time to their backend servers. But it turns out that can happen when the game streaming server and the backend servers and other players are all in the same data center. That network is really good. By the way, if you have a bug like that, the XGameStreaming is Streaming API lets you detect that a game is streaming to handle that and anything else. But even though you get this really great backend streaming latency, there's still latency to the player. And so that's where existing multiplayer algorithms, we think they still make sense. But instead of tracking the time that the console, which might be in a data center, received multiplayer state or did processing, the important thing is to track the time that the player's device responded using those same average latency or frame displayed APIs. Now let's talk about one other experiment that we've been playing with, and something that we hope will inspire you as well. This is the idea of movement compensation. So let's talk about why I'm bad at racing games. The reason I'm bad at racing games is sometimes you go into a turn and you oversteer. Now, when you add latency, that can get a little bit harder because you don't immediately see the oversteer, and so you oversteer more. And then eventually you see the oversteer, and you oversteer in the other direction. And then you go back and forth, and it gets into sort of a fishtailing motion. So we're going to take a look at what that looks like in our spaceship game, this time running at full speed, but still with artificial latency. So you might have seen the target overshooting as we were trying to stop on the ships. So the experiment here that we tried is, let's see if we can do a little bit of linear extrapolation on the way that the stick is moving to predict what it is that the player is trying to do a couple frames ahead of where they do it. And then when we mispredict, we'll use those same APIs, XGameStreaming getAssociated frame, to backtrack to what the player tried to do on the frame they tried to do it and correct for it. This is going to look a little bit jumpy, and that's on purpose because we aren't doing any smoothing when it jumps back to where it's supposed to be, but you could imagine doing that for a smoother client experience. Let's take a look. So there you could see the aimer was able to stop a little bit more easily on the ships. Okay. So just to recap, here's the toolkit we've talked through today. XGameStreaming gets stream added latency for average latency, like Gears 5. XGameStreaming getAssociated frame for matching frames to input, like button presses to shots. And XGameStreaming getLastFrameDisplayed for frames without input, like Coyote Time. And XPStress for testing. Now let's wrap up our story. With Alex's inputs jumping back in time, every shot counted, and movement was predictable. They could finally play a fair game against the aliens, and fair was all Alex needed to save the Earth. Thanks for coming today. I hope this gave you some ideas. Make sure to check out the rest of the multiplayer track on GameStack Live. Thanks.